So let me introduce you Pascal. So Pascal is a professor of geophysics at the University of Brest in France. His specialty is electromagnetism in many domains. He's also a scientific advisor and co-founder of two companies. One, Imagir, with me, and the second one is MAPEM Geophysics, which is specialized in marine instrumentation for deep and shallow investigations. And today he accepted to present his research in marine electromagnetic for shallow environments. So thanks, Pascal, for accepting the invitation, and please.
Thank you for the invitation. So today I would like to talk about nearshore and near-surface marine electromagnetism to address some scientific and industry questions. So my co-authors are Jean-François Deux from MAPEM Geophysics, Judith Dussart, former PhD students, our late colleague Bruno Marcet from IFREMER and seismic person, and other colleagues who contributed to the various works. So the outline of this talk is about marine shallow resistivity in electromagnetic investigation. And I will show you a few case studies about results on geology with seismic mask and scatterers, which was originally the reason why we developed these EM techniques. And I would like to show you that it's possible to combine EM and seismic, and to some extent bring some constraint to geotechnical investigations. And then I will finish this presentation with an application which are very exciting right now about the coastal aquifers. So the first question is, why use electromagnetism? It's already complicated in land, so it's even more complicated at sea, given the seawater is extremely conductive, and it has been challenging to do that at sea. So electromagnetism in general is a technique like seismic, which gives you some vertical informations using horizontal acquisition systems. So as a result, it's what we call an imaging, vertical geophysical imaging techniques, because you can recover structures in depth with those data. So it's complementary and sometimes works better than acoustic and seismic, because we know that despite acoustic and seismic is used widely, it may fail in some circumstances, particularly at sea when you have small contrast of the seismic parameters, may have strong reflection on hard rock, may have scatterers like shallow gas, and then you need something to bring the information, the missing information. So the EM techniques have been used widely for land investigations in various domains, and they can be used to image subsoil down to depth to a few kilometers if you are using the very penetrating devices. So originally we were contacted by industry in order to face a problem of seismic reverberation of various hard rock in order to image the subsoil for marine environmental and systems to be deployed. And so on the course of this, we started to various research projects. And also on the industry side, we proposed this technique for various type of investigations, like contributing to geotechnical survey for drilling site positioning, etc. And also an important topic which emerged was the localization of cables, pipelines, and unexploded ordnance. So some basic physics for those of you who are not familiar with electromagnetism. So electromagnetic fields are diffusing, are diffusing in rocks and materials and controlled by the electrical resistivity of the medium. In practice, electric currents are either injected or induced in the environment, and they can be collected using direct current or alternate current voltage or electric or magnetic field sensors. Since diffusion is a function of the resistivity, if we can control the penetration depth, then we can have some information about structures beneath the sea bottom. And those penetration depth, depending on the system you are using, range for very shallow depth, less than 1 meter, to several kilometers. So the conduction is well known as what we call resistivity sounding inland. You just inject current between two electrodes, and the electric current penetrate in the ground. That's when you are inland because the air is an insulator. But when you are at sea, a lot of current goes into the seawater, and you need extremely accurate sensors in order to recover the weak signal left that goes into the ground. So the penetration is a function of the offset between the injection device and the electrodes measuring the electric potential. So the longer this distance, the deeper you go. The induction process, which is the other way to access to the electrical resistivity, is the alternate current technique, in which the conduction that we use when we inject current is replaced by induction into a conductor. So you have a time-varying source, and this time-varying source induces electric current in the ground, or when you are seawater, also in the seawater. And with this, you can collect the electric field or the magnetic field related to this induction process, and those fields are related to electrical resistivity. So you can play, instead of playing on the offset, you can play on the offset also to adjust the penetration depth, but you can also play with the frequency of your signal. And the lower the frequency, the deeper you can probe. And so with those devices, you can probe down to also several kilometers. This technique has been quite popular in oil and gas investigations. This is a system used in oil and gas. And the idea, of course, is when you want to do shallow investigation, is to take this system, which is used to probe to several kilometers, to smaller scale, in order to be able to probe to shallow depth. So this was in this context that we developed this streamer, which is a combination of DC, so electric conduction, and AC, electromagnetic induction, using a system which is floated just above the sea bottom. You see, in this system, for instance, you can see that the system is dragged on the bottom. It's extremely slow process. And this system, you have some sensors are on the bottom, so it's not very practical when you know the cost of marine operations. Or it's floated at the surface, which is very far from the ground. So we try to do something in between in order to be able to map very large distance and to do the very large survey, similarly to what we can do with marine seismic. So you inject this current in this dipole, and part of it goes into the ground. You lose some of it in the seawater, but that's okay because it can be modeled accurately. And then we have these receivers behind, and the distance between this injection system and the receivers behind give you somehow the penetration you can reach with the system. So of course, if we don't use very long streamers, the penetration is limited to a few tens of meters, down to a few 100 meters. I will come back to this point later. Okay, so now once you have acquired those electric field, you have to process them in order to get them okay for inversion. So we inverse them, and we obtain electrical resistivity models. So the processing leads to the well-known apparent resistivity, which is what it is called inland operations. You can also use normalized electromagnetic field, and you plug that into your inversion codes, and you can use various 1D, 2D, 3D inversions. We can play with commercial system, and we also develop in-house inversion approaches for specific targets. And so at the end, once you have stored your data, your system, obtain data, you can get this nice image of the underground, and it's scaled in electrical resistivity. And you can see that for those of you who knows about surface land resistivity, you can see that we are not at all in the same order of magnitude. This is something going from 0.2 to 1.2 ohm meters, and when you see at 1.2, we are quite happy because we know it's resistive. So that's make love for everybody working inland. Okay, the acquisition, in order to reach this kind of thing, what we do, we sample like in seismic with seismic streamers and 2-4 nodes. We have electric currents up to 40-50 amps, but it's because we are on seawater, it's very small voltage. It's a few volts maximum, and so there's no harm to the life into the water. And we can shoot quite often, every 5 seconds, which makes the result we can obtain at quite high resolution. So depending on the length of the layout, we can go down to mostly for the nearshore objective, it's in general 30 meters, but we can go a little bit deeper. And with this high rate of data acquisition, we have a resolution of about less than 1 meter. And the vertical resolution, well, has the same problem as inland. It's a diffusion process, and the resolution with depth is about 5% of the depth. So this is an example which triggered the project originally. It was the karstic geology in France, not very far from where we live. There is an area which was emerged some time ago, and it's calcareous medium. And so when it was emerged, it was weathered. So we have a karst, and now it's underwater. And you have this karstic medium with unknown holes, probably filled with water. And so that's exactly where people wanted to deploy MRE, so marine renewable systems. And so with seismics, they could not see anything because the surface layer is calcarenite, extremely hard rock, and there is no penetration for seismic. And so that's why we started to play with this electrical resistivity imaging. And so you have in this image of the electrical resistivity, this is in decimal log, so it's still very small if you compare what we know inland. And the yellow is for resistive, and the blue is for conductive. And you have this very heterogeneous medium with hard calcarenite, weathered calcarenite, and so all these things couldn't be imagined by seismic. And so we saw that with this MRE, this electrical system, we could provide some nice information that was not available otherwise. Another type of structures which are very difficult to image because they are small scatterers, they're very difficult to image with seismic, is boulders. Those boulders comes in many sizes, from a few tens of centimeters to many meters, to more than 10 meters sometimes, and very difficult to localize. And so with resistivity measurements, given that the boulder is pretty massive, and so when a rock is massive, it's electrically resistive. And when it's in the middle of sediments and loose, for instance, in those areas, you have a very conductive medium because it's saturated with seawater. And so you have nice contrast, and you can see those isolated bodies that when you want to deploy MRE systems, you don't want to have to deal with them. Okay, and other type of applications is with looking at sand. Sand is, of course, extremely conductive because it's saturated with high porosity with seawater, and it's mixed with sometimes with rocks which are quite massive, difficult to image with very quick lateral changes, and so that's another application where the resistivity measurements can help to understand what's going on. Finally, in order to be convinced that resistivity is actually seeing geology, since a lot of people think that only seismic can visualize geology, we compare some seismic data with some resistivity data, same area, about location was very close. They were not acquired simultaneously, but they were quite acquired precise as well as possible, one on top of the other. So on top of here you have the seismic sections. When you see the sea bottom, you see the multiples, and you can guess structures below, and you can see that the resistivity observe those same structures very accurately, and you can see the variations of the nature of the rock with the change in the resistivity, which is again red resistive and blue conductive. And so you can see that they are very similar. It's in fact very complementary because, as we know, seismic is very good at localizing and characterizing interfaces, when diffusive technique like EM is not very good. On the other hand, EM techniques are very good at looking inside those layers limited by sharp seismic reflections, and therefore the two of them are very complementary. This is another example where you see the difficulty in those complicated areas to image those structures and also to guess what is between the various layers revealed by the seismic. And by adding the information of the resistivity, you can see variations that you can interpret geologically. So the question we ended to ask ourselves is, finally, since there are some correlation between seismic and resistivity, it would be nice to be able to combine them. So there are various ways to approach this problem. We can use a seismic reflection and guide the marine electric resistivity tomography inversion with those. The problem that the seismic reflection sections are in time versus distance, and the conversion into velocity is not an easy process. If we can do it, it's even better to work directly with the velocity models rather than to use the seismic reflection. This is what we did. Why it is interesting is because the velocity is sensitive to some geotechnical properties. The resistivity is also sensitive to some geotechnical properties, particularly the porosity, and the combination of them makes sense. If we want to be guided by seismic reflections, the interest is, of course, to try to fix the reflectors seen in the seismic reflections in order to better get resistivity inside the horizons. So, can we do the seismic inversion for both of them together? That's still difficult to foresee because the seismic conversion into velocity models is a very difficult and long process, which is difficult to insert into a joint inversion algorithm. Okay, just to show you some what the benefit to have a seismic and and resistivity at the same area. This is an example near Brest. This is Concarneau. It's a very nice medieval city in Brittany. I invite you to visit it if you have the chance. And in this area, you have this interesting place where you have soft mud, a lot of pot marks, and in fact a lot of gas coming. So it's biogenic gas, of course. It's a lot of them. It's a very particular area, and it's interesting to test the problem of gas masking for seismic. So this is one section across this area where you have this is the seismic velocity deduced from the multi-channel seismic imaging with ultra-high resolution system from IFREMER, and superimposed on the acoustic amplitudes converted from time to depth. Now you can see the nice reflections and the velocity in blue and red, and the mask where you don't have any information on the seismic because the gas is a very good reflector for seismic waves. So we did the resistivity section in this area, and as you can see, that resistivity is very colorful. So we are bright red for the resistive medium and blue for the low resistivity. And we can see that the seismic mask is also an area which is well identified in the resistivity, but since the gas is not a mask for resistivity, what we see is the geological structure of the area. So this is just to outline the two amplitude, acoustic amplitude, and the P-wave velocity models, and the gas, the mask, because of the gas bubble in this area coming from below. So how can we proceed in the inversion to obtain some control on the resistivity by the seismic? It's what we call a constraint inversion. So you need to have an inversion code which takes the apparent resistivity obtained from the resistivity, and this is what we call in this thing is called the cost function. Misfit is the misfit between the actual resistivity, apparent resistivity, and the modeled apparent resistivity. Then you also always need some regularization for your code, and this is a constraint brought by the seismic, and it is introduced as a coupling between the velocity and the resistivity. So rho is for the resistivity, Vp is for the P wave velocity, and so we use this correlation, the gradient correlation, for the whole area, and we try to enforce the fact that seismic and the seismic gradient, so the interfaces, and the gradient of the resistivity be correlated in order to emphasize the places where the two parameters change simultaneously. This is a given time. Well, this is a various test that we did for this by looking at these correlations using various type of inversion of the resistivity constrained by the seismic. So it's interesting that you can see that depending on the coupling that we apply and the inverse technique we use, we can see that we see structures inside the area which is completely masked by the gas, and so we can see the structures and the resistivity which follows the structures seen in the velocity, and then it appears in the mask area, but we can see structures in the resistivity, and so we can extrapolate what we want to know in terms of geology in this area where the seismic has lost the information. So what is more interesting is that you can try to correlate those and try to infer some characteristic of the processes. This is comparison between the velocity and the resistivity in all these areas. So there's too many things these figures. And so if we concentrate in these areas and corresponding to A, B, and various letters, what you see in this diagram is that there are correlations, and there are several types of correlations. So we can localize, of course, it's easy to localize where there are gas, just look at the seismic. We can see that this area is really related to the gas, area, while you have two types of correlations, indicating that you have two types of processes acting in this area. So I don't have time to go inside all the results but from that you can compare with geotechnical measurements and bring some insight about the processes acting on the various parameters. So the way forward from this, that first of all we notice that it's very important to collocate seismic and EM, even if it's not exactly the same place. If the area is heterogeneous, of course, you get some differences, and sometimes it's difficult to interpret. So we advocate to be able to do the joint acquisition, EM and seismic, which is possible. We did that with sub-bottom profilers, but not with real multi-channel seismic, but it's clearly possible. Of course, in terms of money, it's even better because you just need one ship for two experiments. And also, we want to improve the resolution and the depth penetration. And instead of using only the DC part of the signal, we want to combine DC and AC, so what we call a control source EM, in order to increase the amount of information in the same area, which will increase the resolution of the resistivity we obtain. And so we are targeting various types of applications. So we've already worked quite a bit on object locations. I know it is of interest for some of you. And also we want to apply it to new projects. I will summarize briefly, quickly. So just to say that when we acquire the data with the MAPM system, we acquire high frequency. So you have both the DC and the AC signal, but only the DC is used for imaging. The AC is used for object detection. And one of the big challenge is this type of bombs that we have a lot of them in the English Channel. They are aluminum, so you cannot use magnetics to detect them. They are very big and very dangerous. And so using EM works quite well. You can see that this guy, this is a profile of MAPM on the AC part. You can see a very strong signal related to this guy, which is buried in the sun. So this is something which has been presented at the ACG Summit on Geophysical Detection of Marine UXO last May. And please, I invite you to go to see the Florent Collin from MAPM Geophysics presentation. Now I would like to finish by showing what project we are working on, which is quite exciting, is the offshore freshened groundwater, so more simply coastal aquifers, where AC and DC electric data can be very useful. So a lot of people are starting to work on this problem of coastal aquifers, given the need to have more water resources, and also the fact that pumping near the coast tend to pollute the aquifer. So you need to understand those systems. And so there have been some work using systems already developed for oil and gas investigations, and using CSEM, so control source electromagnetics, or system using MRT, either the system like MAPM or some land system transformed to be used at sea. But they're scattered. You obtain various type of results, and you really want to improve this. Just to show you the complexity of the problem, this is two aquifers, one in New Zealand and one in off New Jersey coast. And you see in this complicated geology I'm not going to describe, the aquifers which are inside those layers, and of course they continue offshore, and you have no idea how they continue. And so that's clearly what you really want to find out. And so the preliminary results have been obtained in New Zealand and in New Jersey by some teams, and you can see that the fresh water appears like resistors inside the conductive sediments, but you see that it's the yellow blobs not very well defined, and so clearly we need to refine this resolution, and you cannot do it by just using a resistivity technique. And so the project which is coming well, on which we are now working is really trying to integrate the data using, whenever possible, joint and constraint inversions, combining seismic whenever we can get multi-channel and velocity models. We want to use MRT to the resistivity investigations, but really need to add the AC components. If you want to go deeper, you can also use the magnetotellurics. And so we want to combine everything into one workflow, combining this with hydrogeological models and geological, hydrogeological, geophysical parameters together. And this is the purpose of this project. I hope we'll get great results. And I will come back to present those results in a few years. Thank you very much.
All right, thank you so much. Go ahead, Mark.
Hello, Professor Pascal. Thank you very much for the presentation. It's quite interesting. I'm curious about the slide 23. We have the equation of this regularization term, where you introduce the gradient of the VP and also the gradient of the resistivity. Yes, exactly that equation. Well, can you comment how is this possible? Because we are talking about two different physics. So can you comment more about how is this possible to arise this equation if the physics of both both are completely different? So that's why I am a bit. When I saw this equation, I was a bit interested to understand more about the physics behind this.
So you take the gradient, you have a section of gradient of the velocity, and then when you do your inversion, each time at each step of the inversion, you get your resistivity distribution. You take the gradient, and then you combine those two gradients over the whole 2D sections, and you compute the correlation of those two gradients. And by doing that, you emphasize the signal where there are contrasts. For instance, if you have discontinuity, so an interface, a seismic interface, when you take the gradient of the velocity, you will get a maximum at the position of this interface. So if you want to find a similar interface in the resistivity, you enforce to have the resistivity having a maximum gradient at the same place. That's what this coupling term tells you. So you don't have to worry too much about the difference of physics. It's really comparing two images and try to enforce the characteristic of the seismic image into the resistivity.
What is the sensitivity of the apparent resistivity for the MERT method? Is there a paper about it?
There's papers about it, yes. In our case, the sensitivity is, well, we can distinguish between contrast of 0.05 to 0.1 resistivity ohm meters in those marine structures, because differences so small, are quite tells you something significant between the two those different structures. The comparison with the land doesn't work very well because all the scale is reduced, and so given that the resolution of the measurements, it's the data is very small, we can have an accurate sensitivity to very small changes in resistivity, which is absolutely needed given the scale of the resistivity in the seawater. So sensitivity is pretty high, in fact.
All right, thank you. The next question, do you have any experience with combining hydrologic and resistivity modeling inversion? And what is your approach?
Well, let us work with the project which was just funded this year, because that's exactly the purpose. The purpose of it is to combine hydrological model and geophysical model together and try to run some joint inversion. I'm not sure we can go that far, but at least some constraint inversion. The idea is to be iterative. That is to produce the hydrogeological model will produce some geophysical parameters, and we can compare with the geophysics, and then we can adjust the geophysical parameters coming from the hydrogeology in order to match better the resistivity and the seismic in our case. It means that you need to have some laws to convert the hydrological parameters into geophysical parameters. That's the difficult point for that. But the idea is really to be iterative, try to adjust, so either automatically or by hand, but to adjust the hydrogeology in order to match the geophysics.
All right, thank you. Let's see, where was I? The question, would it be possible to get a hard copy of your presentation? I think this recording, the entire meeting, will be available on the SEG YouTube channel in a playlist for our global subcommittee. So you can find it there. The next question, what sort of geotechnical parameters can be derived from electrical methods?
Well, the main one is the porosity. And then we are trying to work in order to bring a little bit more information about the permeability. And we are also trying to understand correlations between resistivity and S waves, which are not available in this study, in order to be able to try to understand, well, not try to understand, to try to obtain some information about the shear coefficients in the sediments or in the rocks. That's the kind of thing we try to do. The big problem is, of course, the scale difference. Geotechnical is very localized, and geophysics, it's a large scale. And so there is this integration of the vision of geophysics compared to the vision of geotechnics. But that's more or less the coefficient, the geotechnical coefficient we try to obtain, yes.
Thank you. What is the depth you can reach for boulder detection? I guess they're...
with the current systems available, about 40 meters, 40, 50 meters. If you want to go deeper, well, if we are still using, if we are using only the resistivity technique, you need to have a quite long streamer if you want to go deeper than 50, 100 meters, but it's possible. That's why you want to move to combine DC and AC in order to, for the same offset, the same distance, be able to go deeper with low frequency mixing. That's the part of the new project we are working on.
All right, thank you. We have another question. The person says, I've been intrigued with the possibility of the joint inversion of shear wave velocity from MASW and resistivity profiling on land for shallow overburden investigation. It seems your joint inversion techniques may be applicable to this land case. Do you have thoughts on that?
Yes, something we would love to try that at sea. There are people doing surface wave at sea, not so many companies, but some, and we would like to be able to have a joint acquisition, so we can combine S wave and resistivity. And coming back to the previous questions, try to infer some more geotechnical information by this correlation. That's clearly at sea it's more complicated than at land to do MASW. So, but we are not giving up. We want to do it.
All right. We have another question. What line spacing would be required to map a 10 by 30 kilometer area for submarine groundwater discharge in water depths from 3 meters to 20 kilometers? That seems really deep.
You want me to answer that in 10 seconds? But I invite the person to send the question to my address. And you have my email here.
Yeah. I guess
Send
we have
yes.
Yeah. I'll put my email in the chat, and anyone who wants to ask you a question can send it to me, and then I will send it on to you.
Sure. Yeah, please, we're welcome.
Yeah.
Particularly, also someone were asking about references, and we're happy to send references to that person. Yes.
All right. The next question starts with a statement. Thanks for the presentation. And then the question: can you summarize the advantages and inconveniences of AC versus DC implementations?
Okay, the advantage is that, of course, you increase the spectrum of the data. So you because you mix DC and AC. And the DC property is not strictly equivalent to the AC property in modeling and on the imaging. And so combining the two is quite fruitful, but it's difficult because in general there are two different equipment completely. And so that's why we want to do it with our equipment, which does both. So that's the advantage. The inconvenience is that AC is very complicated to model compared to DC. So when you want to do the inversion, the data inversion, it takes a lot of time, and it's complicated process workflow to do it. That's for me. I'm sure people doing CSCM every day will say, no, it's very easy, but it's not so difficult, extremely time consuming. So that's for me the big limitation with the AC compared to the DC.
All right, thank you. So Pascal, thank you so much for your presentation. It was wonderful. That's it for today. I'd like to thank Pascal again. Sorry for the team's challenges. I'm glad that you were able to overcome them. No, it's teams. It has a mind of its own. But I definitely appreciate your persistence in trying to get in here. So thank you so much for a wonderful presentation. Thank you, Sophie, for arranging this, and thank you all for attending. And so look for our social media posts for our presentation for next month. And until then, have a great day. Thank you so much.
Thank you. Bye-bye.
Bye-bye.
Bye-bye to everybody.
Au revoir.